So hi everyone, I'm Aditya Parameswaran. I'm an assistant professor at the University of Illinois. I've been there for a couple of years now. Thank you to Abhishek for inviting me. My pleasure to be here. I'm going to tell you about 3 tools for human-in-the-loop data science. These are 3 tools that we've been building over the last couple of years. And of course, there have been many contributors to these tools spanning PIs, so professors at a number of universities, PhD students, master students, and undergrads. So there have been many people who've contributed to these tools. I'm going to tell you about these 3 tools today. And I would be remiss if I didn't mention our funding sources, Google, Siebel, NIH, and NSF. Okay? So let me start by saying that most work in the database community, which is a community I come from, is what I consider to be myopically focused on scale. Okay? The ability to pose SQL queries on larger and larger data sets. So my claim, so this is a bold provocation, is that scale is a solved problem. Okay? So there was this fun paper that was published a couple of years ago that was called "Nobody Ever Got Fired for Using Hadoop on a Cluster." So this is a paper that was published a couple of years ago, and had a bunch of very interesting findings. Findings like the median job size at Microsoft and Yahoo was 16 gigs. About 90% of the jobs within Facebook are less than 100 gigabytes. Right? So, and these are job sizes that can be easily handled within current database systems. Right? So you don't really need to throw the works at these problems. So the bottleneck is no longer our ability to pose SQL queries on larger and larger data sets. Right? Of course, there are exceptions. Right? I call these the 1% of data analytics needs. So things like large scientific data sets, or the largest data sets at Microsoft, Google, Facebook, LinkedIn. Right? So what is a bottleneck then? Right? So if the bottleneck is not scale, scale is no longer the bottleneck. What is a bottleneck? The bottleneck, in my opinion, is actually the humans in the loop. Okay, so as the data set size has grown, what has stayed constant is our time available for analysis, the load that can be taken on by humans, the analysts, and the skills to extract value from data. Right? So both programming skills, analysis skills, statistics skills, and so on. Right? So there's a severe need for tools that can help analysts, both expert and novice analysts, extract value from even moderately sized data sets. Right? So this is really the need of the hour. So there was this article that was published a couple of years ago at CACM. It was called "Big Data and Its Technical Challenges." This was written by an eminent team of database faculty, and it had this wonderful quote. It said, "For big data to fully reach its potential, we need to consider scale not just for the system, but also from the perspective of humans. We have to make sure that the endpoints, the humans, can properly absorb the results of the analysis and not get lost in a sea of data." So I think this is a great and very poignant, very important quote. And this is sort of the guiding principle for many of the research that I've been doing. So the real need of the hour is human-in-the-loop data analytics tools. And human-in-the-loop data analytics tools are characterized by 3 properties. First, they treat both humans and data as first-class citizens. Second, they try to reduce human labor, time, and tedium. Third, they try to minimize complexity, the skills required to extract value from data. Right? So both statistics skills, programming skills, and so on. And HILDA tools, human-in-the-loop data analytics tools, draw from expertise in 3 separate disciplines. So interaction, or HCI, because you need to take the human perspective into account. Data mining, because you need to go beyond SQL to the more human-centric needs. And databases, right? Because scalability and interactivity is still paramount. Right? So the need of the hour is building these human-in-the-loop data analytics tools. And these human-in-the-loop data analytics tools firmly operate at the intersection of interaction, data mining, and databases. So they draw from skills from all 3 areas. So we've been working towards what I call a Maslow's hierarchy for human-in-the-loop data analytics. So how many of you here are familiar with Maslow's hierarchy? Or how many of you are not? Okay, good. So there are a few who are not familiar with Maslow's hierarchy, so I'll spend 30 seconds explaining what Maslow's hierarchy is. So Abraham Maslow, an American psychologist, came up with the theory that human needs can be depicted in the form of a hierarchy. Okay, so he claimed that human needs could be depicted in the form of a hierarchy with the basic needs at the bottom and the more complex needs at the top. So you start with things like the need for food, the need for water, the need for shelter, right? And then you go to the slightly more complex needs, like the need for relationships, the need for family. And then you get to the really complex needs, like self-actualization, right? Which is fulfilling your true potential, right? So this is Abraham Maslow's theory. This is a Maslow, what is called a Maslow's hierarchy. He came up with this in 1943. And some of you may have seen the 21st century version of this hierarchy, where the need for Wi-Fi trumps everything else. That's the first and fundamental need, right? So we've been developing a Maslow's hierarchy for HILDA, or Human in the Loop Data Analytics, where this hierarchy is organized along the increasing sophistication of analysis. Okay, so that is the driving principle for this organization. And so we have 3 tools at each of these tiers in the hierarchy. We start with the basic skill, right? So just being able to open your data sets, being able to touch and feel your data sets, being able to make small modifications on your data sets, right? For that, we have a tool called Dataspread. And then you move on to being able to play with your data sets, extract interesting insights from your data sets, right? And view various aspects of your data sets. For that, we have a tool called ZenMessage. And then lastly, to record the results of your analysis, share them with others, and then collaborate on analysis. For this, we have a tool called Orpheus DB. Okay, so over the next 3 slides, I'm going to give you one slide summary for each of these 3 tools. These are the 3 tools that we've been building over the last couple of years. So let me start with Dataspread. So as the name indicates, Dataspread is a spreadsheet tool, but it's also a database. So it's a spreadsheet database hybrid. So Dataspread, the goal of Dataspread is to combine the flexibility, ease of use, and sort of intuitiveness of spreadsheets with the scalability and power of databases. So it maintains the front end of a spreadsheet, gives you the power of a database. Okay, so the goal here is to enable what I call the 99% of people who have access to data but are not performing data analysis to be able to just open their data sets, look at it, make small modifications, ask simple questions, right? So that's Dataspread, that's the first tool. The second tool is ZenMessage. So ZenMessage is 2 parts, Zen and Envisage, and this is a tool for effortlessly visualizing interesting insights from your data. Okay, so the goal of ZenMessage is to be able to fast forward to interesting insights without having to do much work. The analyst simply has to specify what they are looking for, and the tool will do the rest, or at least that is the goal. The last tool is Orpheus DB. Orpheus DB is what I call a GitHub for structured data. The goal is to build a system that can manage dataset versions, be able to query across them, retrieve them, and serve them at scale. Okay, so this is the last tool. So this talk, I'm going to spend about 10 minutes per system, maybe a little bit less if we're running out of time. I'm going to tell you about the overview of the system, our vision, why we are building such a system, the architecture of the system, and maybe one key technical challenge that we've had to address in building each of these systems. And the common theme here is that databases are remarkably robust beasts with decades of engineering experience. And so if you torture databases enough, you can get them to do what you want, right? So we are basically leveraging all of the vast expertise that come with these, in some sense, very mature beasts, right? Any questions at this point before I launch off into my first topic? All right. So let me start with Dataspread, right? So the motivation for Dataspread, like I mentioned, is that most of the people doing data analysis and data manipulation are using spreadsheets, right? This is across the board in businesses, governments, academia. Heck, even I use spreadsheets all the time, right? So why do we use spreadsheets? Well, A, it's easy to use. There's a direct manipulation interface that allows you to just go and muck with the data. There are built-in visualization capabilities, right? So you can visualize whatever you want, and it's flexible, right? So there's no need for you to declare a schema in advance. But at the same time, we are all of the opinion that spreadsheets are terrible, right? Everyone thinks that spreadsheets suck. Why, right? The first reason is that spreadsheets are really slow, right? So we've worked with spreadsheets where a single change can lead to wait times of a minute on a 100,000 cell spreadsheet, right? Remarkably slow. Second, we can't even open spreadsheets beyond 1 million cells. Most spreadsheet software will just simply say, sorry, we can't handle that, right? So 1 million cells is typically the limit for most spreadsheet software. So speed by itself can prevent analysis of data. The second reason is that spreadsheets are tedious and not powerful, right? So if I wanted to do a filter, I have to do it via copy paste. So let's say I was working with a spreadsheet of student grades, right? And I wanted to figure out, of the students who did badly in the midterm, are there other factors that have affected their performance? For me to do this, I would have to copy paste each of those students that meet the criteria to a special or a separate area of this spreadsheet and then perform the analysis there, right? So this is really tedious and painful. Arbitrary joins are impossible on spreadsheets. The only form of joins that are supported are foreign key joins, and that too via a really clunky mechanism via VLOOKUPs, right? So that is the only way you can actually get joins to execute on a spreadsheet. The last issue is that spreadsheets are remarkably brittle and error prone, right? So collaboration on spreadsheets typically happens by sharing spreadsheets around, right? With no collaboration or recovery mechanisms built in, right? So most of these issues around brittleness and error-prone nature have led to the retraction of several psychology and economics papers over the years because of errors that were discovered later, right? So using spreadsheets for collaboration is painful and error-prone. So now let's turn to databases, right? So does databases solve all our problems? So databases are certainly scalable. They're powerful and expressive. You have the power of SQL behind you, and they are collaborative. They have recovery mechanisms built in, and they are succinct, right? A single SQL query can replace hundreds of thousands of formulae. So why not use databases? Well, for the same reason why spreadsheets are so useful, right? Databases are not easy to use. They don't have any built-in visualization capabilities. They are not flexible. They have to obey a rigid schema, right? So the question is, can we combine the benefits of spreadsheets and databases with spreadsheets as a front-end engine and databases as a back-end engine? And can we retain the benefits of both? It turns out the answer is that it's not that simple. Okay, so spreadsheets and databases have fundamentally different ideologies. Okay, so it makes integrating spreadsheets and databases much like gluing an apple to a pancake, right? So these are two just very different mechanisms. Let me give you a few examples. So when it comes to data models, databases are schema first. You have to declare your schema up front before you do any modification or manipulation of data. In spreadsheets, there's no need to declare a schema, right? So it's completely dynamic, completely ad hoc. In databases, you address tuples via address data via tuples using primary key. In spreadsheets, you refer to cells via row and column, via the position, right? Databases have no notion of presentation, right? No notion of order. It's completely set oriented, completely unordered. Spreadsheets, on the other hand, have a notion of order, right? The cells are laid out in a certain way, and a user is viewing a certain window in their viewport, right? So these are three examples of why the integration between spreadsheets and databases is fundamentally hard, because these two are fundamentally different beasts. Okay? So I'm going to take the next 3 or 4 minutes to tell you about one problem that we addressed in this regard. This is a problem of representation. So how do we represent spreadsheet data within a database is the question, right? So let me start with a spreadsheet that looks like this. I know many of you may not be able to see the values in a spreadsheet, but hopefully you understand that there's some data sitting on the spreadsheet. So at one extreme, if I have a fairly dense spreadsheet, then I can store that dense spreadsheet as a table within the database, right? So I can simply store it as a table with attributes corresponding to the row number, the value corresponding to column 1, value corresponding to column 2, and so on and so forth. On the other extreme, if I have a spreadsheet like this where the values are spread out, I can store it as triples, right? So I can store the row number, the column number, and the value, right? So I can store it as triples as opposed to storing it all within one table. So the question then becomes, can I do better than these two extremes? And turns out the answer is yes, you can do better than these two extremes. And how do we do that? Well, given a spreadsheet like this, I can carve out the dense areas and store them as tables, and then carve out the sparse areas and store them as triples, right? Sounds easy enough. So if I have a spreadsheet like this, maybe I will carve out, instead of storing all of the spreadsheet in one table, I can carve out this vertical slice and place it into one table, that vertical slice and place it in another table, and maybe this one item in the middle I'll store as a triple, right? So maybe that's one way I could decompose this spreadsheet and store it as tables in the database. Unfortunately, even if we only use tables, carving out the ideal number of partitions, minimizing a combination of storage, modification, and access costs is actually NP hard, right? So this uses a reduction from the minimum edge length partitioning of rectilinear polygons. Rectilinear polygons are polygons where the edges are aligned to the x or y axis. Okay, so this means that this problem is fundamentally hard. So what do we do, right? Do we have a way out? And thankfully, there is a way out. The way out is to constrain the space of partitioning. So instead of considering all possible partitionings, I'm going to use a constrained set of partitionings. These are partitionings I call recursive decomposition based partitionings. The idea is very simple. So let's say this is my spreadsheet area. I can decompose this spreadsheet area into two areas using a cut, a vertical cut in this case. And then now I have two spreadsheet areas, right? What do I do with those two areas? I might choose to use this line to split this spreadsheet area into two, and this line to split this spreadsheet area into two. And I keep going, right, until I've come up with, or I've identified the partitions that I want to then store within my database. So as you can see, this is a very natural class of partitionings, right? So they're fairly natural. So the question then becomes, what am I missing? Are there any partitionings that I'm not considering if I only consider recursive decomposition? And turns out the answer is yes, there are partitionings that we are missing. So let's say I have a spreadsheet like this where the filled in cells have been annotated with stars, and I want to partition this spreadsheet into these four portions, four rectangular portions. If you take like 30 seconds to stare at this example, you will come to the same realization that I did, that there is no way you can come up with this partitioning via just recursive decomposition. Okay? So we are missing some types of partitionings, but it's not a deal breaker because these sorts of partitionings happen very, very rarely. So it turns out the optimal recursive decomposition based partitioning can be found in polynomial time using dynamic programming, right? So this is good news. Unfortunately, this dynamic programming algorithm is still quadratic in the number of rows and columns. So that makes it infeasible to apply it on large data sets. And the way out is to merge rows and columns that have identical signature, right? So merge the rows and columns that have identical signature, operate on the compressed representation, then the time to find the optimal recursive decomposition based partitioning roughly boils down to the time for a single scan. Okay? So great. So we have a solution for the representation problem. And I promise this is as technical. Actually, I might get a little bit technical a little later on in the talk, but this is one of the most technical pieces in the talk. So hopefully I didn't lose a lot of you. Okay. So how have we been building this system, this Dataspread system? We've been using Postgres as a backend and ZK Spreadsheet. This is an open source web-based spreadsheet tool as a front end. And Dataspread comfortably scales to an arbitrary number of rows and can easily handle SQL queries. Here is a screenshot of Dataspread in action. And I know even I can't read these numbers, so I wouldn't ask you to read the numbers, but I've highlighted just one number, which is the row number here. And as you can see, I'm operating on a row which is greater than 1 million, right? So this is already beyond the capabilities of current spreadsheet systems, right? So we have already, in some sense, beaten current spreadsheet systems in terms of being able to work with large data sets. So hopefully, our efforts in building Dataspread will bring spreadsheets from, in some sense, what has been an era of development in the 80s and the 90s to the big data era, right? Being able to work with spreadsheets on very large data sets, that's our goal. Okay, that's it for Dataspread. Let me move on to my next topic, which is ZenMessage. Okay, so once you have your data set loaded into a tool where you can look at visualizations on the data set, that tool could be Excel, that tool could be Dataspread, that tool could be Tableau, right? The standard data analysis recipe goes as follows, okay? You typically select a visualization to be generated and then see if that visualization matches what you had in mind, matches the visual criteria that you had in mind, and then keep repeating this until you find a match, right? This is what a lot of data analysts do. They just keep looking at visualizations day after day, right? And for instance, let me give you a concrete example. If I wanted to find a product whose sales over time spiked on March 15th, the way you would do this within Tableau or Excel is to generate a visualization for every single product and then keep stepping through until you find the product that has the criteria or matches the criteria that you had in mind. In this case, a spike on March 15th. Okay, so doing this when you have a large number of visualizations is tedious, extremely tedious and time consuming, right? Because you have to manually go and examine each of these visualizations to see if they satisfy the property that you care about. So the key issue is that we have a large number of visualizations. Visualizations can be generated by varying the subset of data that you operate on and varying the attributes that you're visualizing, right? So, and you have to look at all of these visualizations in order to find desired visual trends or patterns. And turns out this is a real problem. This problem appears everywhere. And here are 3 concrete groups that we've been partnering with to test out our solutions. So the first is advertisers at Turn, an ad analytics company, and they have a need to find keywords with similar click-through rates to a specific one as one of their examples. Bioinformaticians at an NIH-funded genomics center want to find aspects on which two sets of genes differ. Battery scientists developing lithium-ion batteries at Carnegie Mellon want to find solvents that have sort of desired properties. For instance, one of their goals was to find solvents for which a certain physical property has a hockey stick shape. Okay, this was one of their needs. And a common theme in all of these use cases is that finding the right visualization can take several hours of combing through a whole bunch of visualizations manually. So our key insight in building or developing ZenMessage is that we can automate that search process. So instead of combing through these visualizations manually, individually, one at a time, you just tell us what you want and we will fast forward to those desired insights, or that's the goal at least. And so here are some desired properties for this automation. First, ZenMessage should be expressive. You should be able to specify what you want or care about. You should be able to interact with the results and then specify follow-up queries. And it should be scalable, right? You should be able to work with very large data sets. So this is our goal, or these are the properties that we've been focusing on in developing ZenMessage. So our ingredients in developing ZenMessage are the following. First, we have drag and drop and sketch-based, pen-based interactions to specify and find desired patterns. We also have a sophisticated visual exploration language that you can use to ask more complicated queries. For instance, if I wanted to find products whose sales over time has been increasing while profits over time has been decreasing, I can use a ZQL query to do that. It's just a couple of lines. Okay? Then you have a scalable visualization generation engine that allows you to examine all of these visualizations at scale and find the ones that you would care about, as well as rapid pattern matching algorithms that go within to sort of use sampling to speed up the search even further. So here's a screenshot of ZenMessage. On the left-hand side, we have an attribute selection interface. Here's when you would specify which attributes you care about. As soon as you've specified which attributes you care about, on the right-hand side, we show you typical trends and outliers for those attributes. Okay, so for instance, one of those typical trends is the trend for Panama City, which says that there are a lot of metros in this case that have this spike for sold price by quarter. That's the data that I'm visualizing. So this is a real estate data set. I should have mentioned that earlier. Real estate data set, I'm looking at sort of sold price by quarter. These are 3 representative trends for sold price by quarter, and these are 3 outliers. Okay. Right. So next comes the sketching or the drag tools on which 2 groups of data differ the most. Okay. So this is one specific instance of a query that can come from such a system. Right. Of course, our system is tailored to handle all sorts of queries, but I'm telling you about one specific query. So here are some examples of how that query might be useful. I might want to find visualizations on which 2 solvents differ from each other. These are physical properties that might be of interest, or visualizations on which product X differs from product Y, right? And I'm going to use this as my running example. Maybe I've found that product X is doing really well while product Y has been doing badly, and I want to find the reasons for that difference, right? So these might be sort of cues towards finding why there is a difference in performance. So, and I'm going to represent a visualization using a triple corresponding to the x-axis, the y-axis, and the aggregate. Okay, so this is the dimension d, which is the x-axis, the measure y-axis, and the function, which is the aggregate that I'm applying to the y-axis. And here I'm grossly oversimplifying what it means to be a visualization. There are many different knobs and parameters that you have to set to specify a visualization, but I'm boiling it down to the 3 most important ones. Of course, there are others like how do you do the binning, how do you do the interpolation, how do you deal with missing values, how do you, can you go with 3 or more dimensions for the visualization. Right now I'm just doing 2. Right? So each triple corresponding to a DMF on a specific subset of data can be easily computed using a single SQL query. This should not come as a surprise. This is a simple group by query. So the naive approach to find visualizations on which 2 groups of data differ the most, the naive approach is simply to, for each triple, each DMF, compute the visualization for both products. Right? So here I'm computing the difference between products. I'll compute these visualizations for both of these products and then compare those 2 visualizations, and I loop, right? I do this for every triple. This is the naive approach, if you will. And so I glossed over one aspect here, which is how do you compare, and for this you can use a utility metric. There are several sort of standard distance metrics that we can borrow from for this purpose, so I'm not going to talk about this in my talk. The issue that I'm going to talk about in the talk is the issue of scale, right? So if you have tens of dimensions, very reasonable, tens of measures, and even a handful of aggregates, you have hundreds of queries for a single user task. So the user just told you one thing to do, that one thing has spawned hundreds of queries, right? So it's going to take a really long time to get the results for which pairs of visualizations sort of distinguish these 2 sort of groups of data the most. So there are 2 issues with the naive approach. The first issue is that you're repeatedly processing the same data across the queries. And the second is that you're wasting a lot of time on the low utility visualizations. Visualizations you're not even going to show to the user eventually. And so we've come up with a bunch of optimizations for both of these aspects, some sharing based optimizations for the first aspect and some pruning based optimizations for the second aspect. Okay? So in the interest of time, since I have just 10 minutes left and I want to leave some time for questions, I'm going to skip ahead beyond this. I'm happy to point you at the paper for the details of how we did the optimization. Okay? So suffice it to say that our optimizations lead to hundreds of, so several 100x speed up on both small data sets as well as large data sets, bringing this sort of query within the realm of interactive time. So that was ZenMessage. Once again, it's a visual data exploration engine. Next, let me move on to Orpheus, right? Orpheus DB. So the motivation for Orpheus DB is that everyone who has access to data is doing collaborative data science, right? So there are many teams of individuals that are working on data sets. They are performing analysis and generating new versions of data sets, right? Maybe they might do some normalization. Maybe they will drop a column. They might add some rows, and so on and so forth, right? So everyone is working on these data sets, often as a team, and they're generating many, many versions as a result of their analysis. And typically, and I'm not saying this is true across the board, typically the way these data sets or data set versions are stored is within a shared file system with all of these data set versions just placed within that file system. Okay, so that's what is typically done. And often the relationships between these data set versions are completely unknown. You just know that there are these versions that exist, right? So XKCD had a fantastic comic about this. It said, never look in someone else's documents folder because we are really bad at keeping track of documents and files and data sets. Okay? And this sort of sloppiness sort of leads to problems in data science. So the challenge is, can we build a version data store? Can we build a database system that can store data set versions, be able to efficiently store them, efficiently retrieve them, and efficiently query across them? So let's start with some obvious starting points, right? So the first starting point is standard version control systems, right? You can use Git or SVN as a starting point, right? Unfortunately, both Git and SVN, while they are great for source code version control and version control of relatively small files, they are both inefficient and unsuitable for data set version control, right? First off, they have an ordered semantics, while data sets don't have any order, right? The tuples could be ordered in a different way and it's still the same data set. They have no data manipulation API, right? So the set of commands that you can issue via Git or SVN is very restricted. There's no efficient multi-version queries, right? So you can't really query across versions very easily. And they have pretty poor support for massive files, right? I know that there are some recent initiatives by Git, for instance, to deal with large files, but effectively they don't do anything with them. They don't really try to sort of efficiently store them, efficiently retrieve them, and recreate them. So this is the Git large file sort of software. And of course, there are database systems which don't support versioning but are efficient and scalable, right? So these are two potential starting points. So for Orpheus DB, the way we've been building Orpheus DB is to combine Postgres, which is a standard regular old database system, the same database system we've been using for the other projects, and add versioning capabilities, right? Can we add versioning capabilities within Postgres? So let me tell you about one challenge that we encountered, and unfortunately I won't have the time to tell you how we solved it, but I'm happy to point you at the paper like before. So for dataset versions, you often have thousands of these dataset versions at various stages of analysis, right? And each of these versions could have millions of records, right? So at one extreme, you could store each of these versions independently, right, as a separate table within my Postgres instance. And this could be really good for accessing these versions, right? You just need to read that one table in order to access a specific version, but it would be a huge storage cost. The other extreme, you store one version and then store all others as deltas, right? So all others as deltas to either that version or to other versions. So you have a chain of these deltas. And so this can be pretty compact because you only need to store the deltas as opposed to the actual versions. But the version access time can be really high, right? In order to recreate a specific version, you might need to follow a whole bunch of chains of deltas in order to recreate that version. And also, we want to answer queries, right? We want to be able to ask queries like, retrieve the first version that contains this tuple, or show me the history of the specific tuple, or find me all pairs of versions where there is a large number of tuples that were added, right? And these are the kinds of queries that we want to ask. Git, for instance, has no capabilities that would support any queries like this. So our framework, as we are building it, our framework is the following. We have a user interface layer on the top Currently, it supports Git as well as SQL queries on specific relations. We have a versioning layer in the middle, which does parsing and translation, translates queries from the user interface layer into queries that are understood by the database system. We also have a layout optimizer that tries to use indexing and partitioning schemes to cleverly arrange the data so that it's easy to retrieve data on demand. And the Postgres backend is completely unaware of versioning. It just doesn't even know that versioning exists. Okay. So with that, I've hopefully given you a flavor of each of these three systems in my Maslow's hierarchy for human-in-the-loop data analytics. I've told you about Dataspread, I've told you about ZenMessage and Orpheus DB. We are actively developing all of these tools. We are coming to the point where we would love to have users try out our tools, see what they think, and we have websites dedicated to all of these tools. My website is here. I'm on Twitter. Happy to take questions. Yep. Sure.
Lovely talk, Aditya. The question I have is, you talked about data mining, but I didn't see that. Even machine learning, I mean, the problem you talked about can be posed as what is the features that distinguish this class from that class? And clustering, subspace. So what role do you think that plays, where you look at the data not as data, but as representative of some distribution which actually exists in the world?
Got it. So the question is, firstly, what is the role of machine learning and data mining within these three tools? And secondly, how do I think about data distribution and how does that impact either the usability of the tools or the design of these tools? Would that accurately capture? Okay. So certainly, I think for some of these tools, the target demographic that we are going after are people who are not expert programmers. For Dataspread, I'm not even going after the programmer demographic. I'm going with people who use Excel on a day-to-day basis, but aren't able to open their large files. For instance, we work with some bioinformaticians, and they work with biologists, and the biologists generate the data, but are not even able to look at it. So they send it to their friends who can say, hey, yeah, data looks all right, right? And so just being able to open the data and stare at it can be a substantial improvement to their current existence. So yes, so there are some aspects that are tailored towards non-programmers rather than, let's say, machine learning experts or data mining experts, which happen more towards the top layers of the hierarchy. Orpheus DB, in some sense, is targeted at those people. So ZenMessage and Dataspread, to me, largely cater to the non-programmers in the crowd. Orpheus DB is catering to the machine learning or data mining experts. Now, the second question is about distributional assumptions. So so far, we've been thinking about how those distributional aspects can help tune our utility models for ZenMessage. For instance, if I wanted to find if two things are actually similar or not, how do I do that, right? And we've been thinking about how to sort of take sort of the status quo rather than just blindly applying a distance measure. Can we use some understanding of how the data actually looks like to influence our distance measure? And that's where we've been thinking about how machine learning and data mining plays a role, at least in that aspect. Largely, a lot of these fundamental primitives for ZenMessage, like pattern searching, similarity search, clustering, often also borrow from data mining primitives. So that's another way where data mining plays a role. Does that answer your question? Sort of. Sure. Yeah.
Thank you, Aditya. Very interesting talk.
Thank you.
So on the first tool that you presented related to Dataspread, because Spreadsheet is such an ad hoc tool, people are putting basically data in the various formats, and they're making a lot of assumptions.
Yep.
And they have sometimes semantic assigned in their mind that, okay, my data here is actually related to data here. Mm-hmm. And the data basically partitioning approach that you talked about, and having in mind that you talked about human in the loop, you didn't talk about actually how to put human in the loop to give you that semantic knowledge overlay to actually maybe sometimes even helping with the actual table design, because depending on the table design, some of the queries, if they are related to each other, they end up in different tables. So what do you think about those?
Great question. So the question is, the partitioning scheme that I described is in some sense agnostic to the humans, right? I mean, I talked about, hey, we should be thinking about humans in the loop, but I didn't really think about humans when I did the partitioning. I just looked at the data and didn't think about semantics, and then tried to optimize for, let's say, storage access or modification, right? So, so that's a great point. I think we do need to think about the role of humans in the loop. So humans can contribute in two ways, and both of which can be incorporated into our model. One is they embed formulae. If they are embedding formulae, they are giving you clear indications that these two data items are related in some way, and I want to compute some statistic or aggregate. So it would help to keep all of them together in one table rather than split them. So that's one, in some sense, direct way humans are, rather actually I would call it an indirect way humans are telling us that this data should be separated. A more direct way is for humans to actually tell you that this is a table. They can carve out a portion and say, look, I want to treat this like a regular old database table, and so I'm going to obey the semantics which come with database tables, and they can explicitly give us that information, and we'll partition that and keep that separate from all other tables. So those are the two ways. Definitely there are a lot of interesting questions in looking at spreadsheets and automatically trying to infer the semantics. That's a great research question. Not gotten to that yet.
So does anything go back down the hierarchy? Like what are sharing and collaboration learnings from the Orpheus DB that go back into your design and further elements that
right. So the question is, do the learnings from each of these tiers help the other tiers, right? So in some sense, I've talked about a bottom-up approach of saying, let me start with the simplest use cases and then develop tools for them, and then slightly more complex, right? Ultimately, the goal for me is to combine all of these tools. Right now, it's like in silos, right? They are independent beasts. They don't really talk to each other. And I think there are immediate users for each of these tools at each level of sophistication for analysis, right? At the bottom, we have complete non-programmers who have no access to their large data sets. In the middle, you have people who have large data sets. They don't really know how to ask queries on that. They are stepping through visualizations manually. At the top, you have people doing data analysis. They know how to do data analysis, but they don't know how to record and make sense of their data set versions, right? So I think right now, we have target audiences for each of these tools. Ideally, I'd like to see some sort of combination where you don't really need to go outside of these tools, right? Right now, there's no interoperability. They're just sort of silos. But ideally, I would like to move towards that. All good? All right. Thank you so much for paying attention.